The title of my talk today is The Mystery of Light. It's very mysterious indeed, as you will see. Now, if you want to learn about light, what you really should do, you should come to MIT and take some courses. The first time that you will encounter light is when you take in your freshman year course 802. A stands for physics. It's electricity and magnetism. And when you have taken that course, you have some idea what light is. And then in your sophomore year, you take 803. That's the course, the physics of waves and vibrations. And then you have a much better idea. But then you take quantum mechanics, 804 and 805. And once you have taken quantum mechanics, you have no idea anymore what life is all about. And frankly, if you ask me, do you know what light is? My answer is no. No, not really. However, I can use and manipulate all those complicated equations that I've seen in all those courses. And they allow me to make certain predictions of what light will do under certain circumstances. Does that mean that I have an understanding of it? No, but I know how to turn the crank. It is a recipe, and I know how to use that recipe. Now, I will try to convince you today that light comes in the form of waves. However, that's not the whole story. I could convince you tomorrow, give another lecture tomorrow, that light is not waves, but that light comes in the form of particles. And that is one of the great mysteries of light, and at the end of my talk I'll say a few more words about that. But my goal today is to convince you that light comes in the form of waves. In the 17th century, it was the great physicist and mathematician Isaac Newton, Sir Isaac Newton, who suggested that life comes in the form of particles. But my countryman, the Dutchman Huygens, he said that they came in the form of waves. And that was a key issue in the 17th century. You're probably all familiar with waves. Water waves, for instance, is probably the most familiar. If you tap on the water with a certain frequency, you get beautiful waves that propagate over the surface of the water. You can throw a pebble in a pond and you also see water waves. So waves move with a certain speed, and so we call them therefore traveling waves. And the speed varies a great deal. In the case of water, the speed can be as low as 1 mile per hour, can be as high as several hundred miles per hour. Depends on various things. The tsunami waves can go as fast as 500 miles per hour. Now, sound is also a wave. I produce sound by oscillating my vocal cords, and what they do, they produce in the air high pressure and low pressure areas. They push and pull on the air. When something moves in this direction, compresses the air, comes in this direction, pulls on the air. So you get high pressure and low pressure areas, and they propagate out to you with the speed of sound, which is something like 760 or so miles per hour. Light is also a traveling wave. Light moves very fast. 300,000 kilometers per second, 200,000 miles per second roughly. The sun is 150 million kilometers away from us, so it takes the light from the sun 8 minutes to reach us. To put that in perspective, even a jet plane could fly to the sun with constant speed. Then it would take 20 years to reach the sun. We have a name for these light waves. It's a very difficult name. I suggest you first hold on to your chair before I tell you the name. We call them electromagnetic waves. Not only light, but there are other forms of electromagnetic waves, like radio waves and X-rays, infrared, UV, all members of the family of electromagnetic waves. So clearly it has to do with electricity, and it has to do with magnetism. Now, you all are familiar with electricity, and you probably know about magnetism. You have magnets on your refrigerator.